So we are live. GM, everyone. How's everybody doing? Let's wait for a couple of seconds and then we will start. So today we have Joran from Infura and he will be explaining us and demoing us Diligence Fuzzing, like how to use Scribble for your smart contract to check it out. Uh, it's a query language for the smart contract to check out the vulnerabilities and other stuff. So, yep. So, Joran, it would be great if you could introduce yourself first.
I will do that. Thanks. Yeah, so just a little bit about myself. My name is Joran. This is my Twitter handle at Joran Honig. You can find me on Twitter, I guess. And I am doing various project-related things at Consesys Diligence. And Consesys Diligence is a sub-team of Consesys, which does many things related to smart contract security. And the two main pillars are kind of audits and tools. Today, we're going to be talking mostly about the tooling part. If you're interested in audits, you can also hit me up afterwards. I'm happy to refer you to the right people. So the main tool that I would like to talk to you about today is going to be Diligence Fuzzing. But before I dive into the details of this specific product or tool, we gotta really look at what this thing called fuzzing is. So the premise is this: you've got some code and you're not sure if it's secure, and this means you gotta check somehow if it's correct and if there aren't any vulnerabilities in there. Generally, you would be using unit test to check for correctness, and you would be doing an audit to make sure that, well, the code is secure. So fuzzing comes into play in kind of like in the middle there, you're doing both correctness and smart contract security. What you do when you use our fuzzer and also other fuzzers, Wrigley, is you'll come up with properties. Properties are kind of like these generic statements about the code that you think should be true. And the key factor here is that you think they should be true. The bugs or vulnerabilities generally happen when your expectation doesn't match reality. One example where this can happen is if you assume oracles work in a specific way and always have up-to-date results, even though they don't actually always guarantee this. The second part of fuzzing, and this is where the powerful part of fuzzing really comes into play, is being able to automatically check these properties that you come up with. So, properties, what are they really? So, you're probably going to be familiar with unit testing. I think every developer should be doing unit testing, and you're probably familiar with it. So the basic gist of it is you have one component in one situation that you run that component through, and you check if it works correctly. So for example, you set up a contract, you call the function under test, add with 1 and 2, and then you make sure that the result you get makes sense. Namely, it should be 3. That is a little bit, it's a nice method of checking specific scenarios, but it's kind of weak because you've only checked the addition of 1 and 2. You haven't even checked adding 2 to 1. So property-based testing, or the idea behind property-based testing, is to kind of separate the check or the thing that you're checking from the actual case. So instead of having one situation that you're describing the behavior of the function. So the way this works, or one example, using the example from before, is if you have the function AND, which takes two numbers, then then obviously it should return the sum of those two numbers. Then the high level property or behavior of this function should be like this English string of, if I call add AB, then it returns the sum of those two numbers. And this is a little bit of a trivial example that I had just now. This is a little bit of a more like specialized or specific example where it's not that easy to write a test for this. So if you have a function that sorts an array, then it should return an array that's sorted, but also that's also a permutation of the original array. Otherwise, it could just always return 1, 2, 3. And it's important to note that you don't need any tool to use this idea of separating the property or behavior from the test case. Here's an example of a test case that I wrote in Python that takes this idea, takes the property of a sorted list, and it separates it into two parts. First, we call the system under test, and then we check the two properties, we check if it's sorted, and we check the permutation property. And I guess it should give some background. So permutation means that the list is basically has all the same numbers in there, or same elements in there, just in a different order or in the same order. So this function applies that idea. And now you can easily write a couple test cases with different types of lists. Maybe, so one you put in an empty list, and one you do one with one element, and one you try with two elements. But the core behavior check, the core property check remains the same. So things stay rather clean. Now, there's different ways to do this in Solidity. You've got Echidna and DevTools and Foundry with their mechanisms, and you can even use JavaScript and Python to write your unit tests, but they all have kind of this problem that it's not, or they can be very effective in their own right, but they all have a problem where it's not always that easy or possible even to write a specific property in Solidity or Python or JavaScript. And that's kind of why we've built Scribble, which is a specification language. And the idea here is that we essentially have built something on top of Solidity, a programming language of sorts. It's a specification language, a programming language of sorts that allows you to write these behaviors down as code comments that can later on be checked by other tools. So here we have a very simple token, an annotated token contract, and it has two properties in there. The first property says, well, the sum of balances is equal to the total supply. And logically, this should always be the case, because we have the total supply variable as a sort of proxy in Solidity to allow us to have the sum of all balances. And this is immediately also a really good example of something that you would not be able to do with pure Solidity, and that would also be quite difficult to do if you use a language like Python or JavaScript to test this code. And this is because taking the sum of a mapping is generally impossible to do. Solidity doesn't keep track of all the keys to a mapping, so you would never be able to do this. And here lies the trick of Scribble. Scribble has a lot of magic in there to make this work and to allow you to do these magic things in a really easy way. And it does so through something that we call instrumentation. And the idea here is we take the annotated token contract in this case, and we take the property, and we create a new annotated token contract that has checks in all the right places in the code and bookkeeping logic to keep track of the sum of all balances. And then it also adds checks to make sure that at any point in time, or at any point that the smart contract might be called actually, that the invariant is maintained. And this just looks like a simple assertion. That's all. Oh, that's very high level how things work with writing properties to be able to do fuzzing. So once you have done this, you have a smart contract with a bunch of checks in there. And this is something that a fuzzer can actually take and automatically figure out everything else for. So we take this smart contract that's annotated and instrumented, and we hand it over to the fuzzer so that it can check all the things and find all the vulnerabilities. And let me just show you what that process looks like. We're gonna stop sharing and move to a different screen. Here we go. Perfect. So I have VS Code or a code space actually set up here with a very, very simple token. It's called vulnerable token. This is a big hint. And there, let me just zoom in because I'm sure that will make things much, much better. And there's a vulnerability in the transfer function. I'll stop it here for a few seconds so people in the recording can pause for a bit, or people watching might already have found the vulnerability in here. But there's a really tricky edge case that actually is a very easy mistake to make if you're writing a token. And there's actually various properties that we could write about this code that will catch this vulnerability, even without you knowing that the vulnerability is there. And let's start by just adding the property that we talked about just now, the sum of balances one. So I'm gonna go in here, add a code comment. And I'm gonna write a Scribble invariant. I can add a really easy annotation, which is a string, describing the property. This is useful for myself, but also later on, the fuzzing report will use the name of the property. And especially once you have like a series of, let's say, 10 properties or so or more, it starts to become really important to actually name them to keep them apart and know which one is failing, if one is failing. So in this case, we want to make sure that this variable, the total supply, is equal to the sum of all balances. So let's say total supply with balances. All right, here we go. And we can take the sum using this argument. So yeah, you can already see I'm using Copilot, and it quickly kind of figures out how Scribble works and what you're trying to do. And it actually provides really good suggestions. You do have to be very careful about coming up with the properties and making sure that what's there actually makes sense. Otherwise, you'll be testing nonsense. So just to recap, we have an invariant, which means this statement will be checked at any point that the smart contract might be called. So this is before every function call or at the start of every function call, but also at the start of any external call. I won't go into too much detail on why this is an important distinction. If you want to know more about that, you can check out our Scribble documentation, which is really easily findable at docs.scribble.codes. And I'm sure like on Twitter, I'll be able to follow up with a couple of links after this is done. So we have the property here. Now we want to do some fuzzing. I set up a really simple script, and you'll be able to do this yourself as well if you do some fuzzing with diligence fuzzing that does some simple steps. It first does what we call instrumentation. So it takes a smart contract and translates it and adds the checks according to all the annotations. Then it will deploy the token to a Ganache node. And this allows us to set up very complex situations with multiple smart contracts if we want. And then we'll take a snapshot of that node and send it over to our API. This sound to be fuzzed. And that kind of sounds complicated. It's not. It's just one command here, namely make fuzz. And you can see it go through the different steps. So fuzz arm is a step where it does the instrumentation. And you should see it change the code.
Yeah, excuse me, Joran. Could you please just increase the font size over there?
Oh, yeah. That's a good point. You can slowly see... Okay. Could you turn off my screen sharing for a bit so I can have my API key?
Yeah. Let me just remove it. Right. Yep.
Yes. Thank you.
No worries.
Just gotta be careful not to leak some secrets.
Yeah. That's the thing about the Web3 space.
I think, it's very easy to create a new API key and revoke it, but can't hurt to add that extra security.
It should not be done, right? It's not a solution, to be honest.
Yeah. Okay. Here we go. Okay, we're good to start sharing again.
All right, so adding it.
Okay. Wrong button. Running the make command again. This time it's a lot faster, and you can see like a lot has changed. And it's actually super fast and already cleaned up. Let me just run this command again that does the instrumentation. Just so I can show all of you through what's actually happening under the hood. So here you can see that we have the transfer function, which is in the same place that it usually is. But you can see that we completely replaced the entire content of that function with something else. Well, what our tool actually did is it took the original implementation and moved it into a separate function that can be called, separately, I guess. And then we added specifically like a little bit of bookkeeping. And then this is the most important thing. We check that the invariants that we wrote are actually maintained by this function. And as we'll see in a minute, it's actually not. There's a vulnerability here. And the fuzzer will be able to find that. Also, another remarkable change is you can see that the way the smart contract uses the mapping, the balances mapping has changed. It uses this weird address to uint library and to and it has functions calls suddenly instead of a pure like vanilla mapping. And this is kind of the magic of Scribble. It adds this wrapper, and this allows us to keep track of the sum of this mapping. It also allows you to write properties that iterate over all the keys in a mapping. So you'll be able to say something like, all the people that have tokens have at least 2 tokens. You would be able to write a property like that because of this magic. Now, whether that specific property actually makes a lot of sense is the question. And before we head over, are there any questions at this point, or?
Let me check it once. Not as of yet.
Perfect.
Yeah.
I hope that means I'm explaining things well.
Yeah, if there will be any, then surely everyone can ask it in the comments.
All right. So let me just show you a few things before we dive into the actual fuzzing campaign and the fuzzing results. So I've set up 2 things to be able to do this fuzzing campaign. I've set up what we call a seed deployment script, and I've set up a fuzzing configuration. The seed deployment script is sounds very complicated, but it's actually very simple. So in this case, we have one vulnerable token that we're deploying to a test network, so a local development network, and we're printing where this token got deployed. For a simple token, it might not be immediately clear why this is useful. But a good example, I think, for seeing where this really becomes a powerful tool is when you start to have systems with multiple components. For example, an AMM. So you can imagine a seed state to be or a seed deployment script to essentially deploy like one AMM contract or one swap contract, and then you deploy a couple of tokens. You mint a few tokens, and you give some of those tokens to the AMM contract, and then like make sure that everything is initialized. And then the fuzzer, when it starts, it actually has a system that's coherent, that's consistent, and that makes sense to start playing around with. Because and this is very, very important, because it's very easy for the system, for a fuzzer to configure a bunch of smart contracts in a way that doesn't make sense at all. And it will have tons of false positives because it will find vulnerabilities caused by incorrect configurations. And usually people are not too worried about those. Because those bugs are generally unlikely to happen. In any case, fuzzing kind of doesn't try to focus on the configuration aspect of a smart contract, but trying to verify that the code is actually secure. I guess in a way it also allows you to check whether your configuration is secure if that's what you use to deploy to this testnet, and if that's what the snapshot that we send over to the fuzzer is of. So that's part one. The other part is our fuzzing configuration. So this is our fuzzing configuration. It's very simple. This is some default values that are automatically generated when you use the fuzz generate config command. So you don't really need to worry about it. This is actually something that's interesting. This is the address of the contract in the snapshot. And this allows us to kind of direct the fuzzer towards specific addresses. Like if you have a seed deployment with multiple addresses and you want the fuzzer to ignore some, this is how you would do it, by not configuring them. We'll use 2 cores for fuzzing. two cores goes twice as fast as one core. That's like the mental model. You can pick up to 4 cores depending on the plan you have with the fuzzing platform. I've
Oh,
set things to end after 10 minutes. Technically, you can run things forever. In this case, we probably find the vulnerability that's in there within a minute, so it doesn't really make sense to fuzz for any longer. But you can set this up to like 10 hours. It really depends. I think there's different use cases that match different time limits. So if you're just developing some new feature, you wrote a couple properties, you want to see if this makes sense. Like you can do a kind of test-driven development with properties. Then you would probably have like a time limit of 2 minutes, 5 minutes, 10 minutes, somewhere in that range.
yeah, yeah,
And in CI, for example, on every PR that you actually want to merge, you would maybe do an hour,
yeah.
2 hours. And then before you're ready to deploy to mainnet, maybe you do fuzz for a day or a week. It also really, really depends on the complexity of your smart contracts. So if you just have a simple NFT token, the fuzzer doesn't need long to figure out how the token works and how to
Right.
trigger all the interesting edge cases. But if you have a really complex lending platform that has tons of features and tons of tricks, then it actually starts to become important to actually give the fuzzer a lot of time to figure everything out. And then there's some simple quality of life things. So setting the project and campaign name prefix allows the platform to automatically categorize the fuzzing campaign, put it in the right place and
Yeah.
store it. And then here we tell it to only consider these source values. So that's also pretty like auto-generated value. If you want to set up a config like this for your own project, fuzz generate config is the command to use. It automatically guides you through setting everything up. All
All
right.
right, all right.
So that's
Yeah,
really all you need to do to start a fuzzing campaign. Let me show you what the actual campaign looks like. Did you have a question, by the way?
yeah. I was asking the same question. Like, how do we start with the fuzzing?
Cool. I guess that's
Yeah,
what I'm gonna answer now. So you start fuzzing by running this command, like the make fuzz command, if you have the script, and which just simply runs the instrumentation, moves everything to Ganesh, and then takes a snapshot, starts things. Really simple. It gives you a link in the terminal. You click it, and that transports you over here. And this is what you'll see. Let me just zoom out a little bit so the formatting works better. You'll get to see this overview. So we can see that the fuzzer is trying 1,000 test cases per second. This is way faster than I would be able to write test cases myself. So big improvement. We see that we achieved a total code coverage of 66%. This doesn't sound like a lot, but I'll show you in a minute that the actual code coverage that we care about is 100%. A simple duration of 10 minutes, like it's been running for around 10 minutes now. And then we have this residual risk parameter. This is a research-based risk estimation technique that kind of allows you to understand how the fuzzer is doing. So the lower this number gets, the safer you are turning off the fuzzer. So 2 minutes on an NFT project will give you like around this number. Well, you might need an hour on like that complex project
yeah,
to get to the same number. And then while I was explaining those things, you probably already saw this graph update. So a fuzzer, how it works is it tries these thousands of random things per second, and it will keep tweaking the inputs that it tries it will try to find tons of different transactions that are possible with your smart contracts. Over time, it will discover more and more of your code base. And we measure this the same way you measure the performance of unit tests, namely code coverage. So if you have 100% code coverage, that means from a fuzzing campaign, that means that the fuzzer hit every part of your code base. All right. Scrolling down a little bit, we get to the most important part of this report, and this is the property summary. So we can see here we had a vulnerable token contract. That's the name of the contract. And then we have the name of the property. The fuzzer did check this property, and unfortunately, it failed. Well, fortunately for me, for this demo, because it actually allows me to show you how the fuzzer works. So we can click here to navigate into the code to see where things happened. So we can see that this function Scribble vulnerable token check state invariance internal was violated. So this is where the instrumentation of the invariance happens. And this is the function that will be called at the end of every function. So make sure that the invariants are maintained. You can see here the check is balance sum equals total supply. And yeah, so we know which property is violated now, but we don't have much to go on to figure out what's really going on. So let me just open this, and we can see here that the fuzzer is giving us an example test case that breaks the invariant, that triggers the vulnerability and exploits the system. It's a transfer, and to be honest, from just this, it's kind of difficult to see what the vulnerability might be. So we have a lot of additional information that you can access, like a stack trace, transaction steps, and transaction details, and even the values of the variables that are used by this property. And in this case, the most important aspect of all of these details, and we give you a lot because, yeah, all of them might be important, is this one. The sender of this transaction, or the creator of this transaction, of this test keys, is this address. And it's exactly the same as the target of the transfer. So someone is sending 19 tokens to themselves, and for some reason that's triggering the vulnerability in this case. So if we go back, and I realize I actually left this, let me open a new terminal. I left this instrumented. So let me de-instrument it, clean it up by running the fuzz disarm command, which is taking a second. All right, we're back to our original contract. So we can now look at the transfer function, and we can see here that this part is a little bit different than your usual implementation.
Yep.
So here, I'll explain the vulnerability. Here, what's happening is, let's actually go through the example. So person A has, let's say, 100 tokens, and they're sending 10 tokens to themselves. So, okay, this works. This also works. Like, they're sending 10 tokens. That's less than the amount of tokens that they have. So this is okay. Now, new balance from is going to be their 100 tokens minus the 10 tokens. So now this is going to be 90. This is going to be 110 because they had 100 before, and now we're going to add 10. So yeah, that's the result. Now we're going to write that 90 to their balance, subtracting the value. And now what you would normally want to have as a behavior is that the 10 gets added back to their balance so that it's 100. But that's not what's happening. We measured the balance of the two address, which is the sender in this case, here before the subtraction actually happened. So what we actually write is 110 here. So we just magically created 10 tokens. And this is kind of an unintentional mint that's happening. And this is an unintentional mint that's not reflected in a total supply, which is why the vulnerability, or which is why the property that we just wrote found this vulnerability. Another property that we could write to catch this vulnerability in this case is this. It's actually suggesting a really nice property. But if the tutor address is a sender, then cool. It actually generates the property for us. That's amazing. But it's wrong. So it's actually okay. This is pretty funny. I have. This is how you know this is not recorded. I didn't try this before, but it actually wrote a property that's correct. It has the vulnerability. It actually describes the vulnerability. So this property would not be violated. What this property says is, if the to address is the same as the sender address, so if someone is sending tokens to themselves, then, so this is the implication arrow, this property must be true. So then the balance of that sender after the transaction, that's what we're measuring here, is equal to their old balance plus the value, which is what's happening. Like if you send 10 tokens to yourself, you create 10 tokens and give them to yourself. This is also the problem of using automated property detection technique or writing techniques, is it might generate properties that are valid for the code, but that are still undesirable. So this is the property that we would actually want to have. If you send tokens to yourself, nothing should happen. And this property would trigger this vulnerability. We can fix this bug quite easily by commenting this out and doing the score from minus equals value plus equals value, done. So this doesn't have the issue. This is because the value that is taken to update the to address is taken at the moment that we added. So this will actually include the subtraction here. But of course, we can run this again, and the fuzzing campaign would not find anything. So a couple of things. We got green bars on the left here. This is the fuzzer's coverage. So you can see it actually, okay, so this is some additional code added by Scribble, but you can see it actually covered all of the functions of our contract that we're interested in, except for the constructor. And this is because that we ran the constructor ourselves when we were creating the smart contract. We didn't ask the fuzzer to fuzz the construction step. And in most cases, you don't want the fuzzer to fuzz this. And this is, you can also see that we essentially got 100% of all the code that we wanted to cover, and the pieces that we didn't cover are kind of like this very specific code that's added through instrumentation combined with the constructor. There's a couple neat features, like something you probably should do if you're developing some open source code is sharing your reports, so you can easily make them public. Anybody can use this link now. And to access this report here, let me see, we can do several things: stop the campaign, download some raw data. Something I really like is our pro mode. This is access. You can access this by default, but we disable it to not have information overload. But we add tons of information about what the fuzzer is doing that allow you to better understand what's happening under the hood. So if you're interested in like what kind of test cases the fuzzer, like unique test cases, the fuzzer was able to determine, you have transaction stats here. So 50% of the test cases were the fuzzer found were for succeeding paths and 50% for failing paths. So the failing paths, an example is require statements. So we found in total 17 different edge cases to trigger require statements. And I should note, not all these cases match up to requires. There's like implicit checks that the compiler sometimes introduces. For example, if a function is not payable, this adds an interesting test case for the fuzzer. Namely, the fuzzer will trigger that edge case by sending a transaction to the contract, executing that function with some money, with some message value. Yeah, and it will store that. Some cool thing. Another cool thing is these 34 interesting paths that the fuzzer found. We have a test case, or the fuzzer remembers a test case for every single path, storing it and allowing you to do incremental fuzzing the next time you run a fuzzing campaign for this smart contract. So it will actually remember everything it found, and it will instantly be able to cover everything again if you didn't change anything. The new parts of your code base, of course, it will need some time to figure out how those work. In this case, incremental fuzzing isn't really necessary. As you can see, everything is covered in the first 5 seconds of fuzzing.
Yeah.
So yeah. And that's really it. That's the summary of diligence fuzzing. You write some properties, some rules about your smart contract, and you throw over your code into our API, and it finds vulnerabilities for you to then go and solve or report.
That's really nice. So if anybody have any queries, like you can check, put down in comments. And yeah. So Joran, I do have a query for from my end, like regarding the properties you said. Would you please like just go to the docs and explain us like how we can understand it and how we can utilize them, different properties.
I'm not sure I fully understand the question. So
Like over here you have checked the invariant, and the below one you have checked out the whether the meth sender that particular conditions, right? So like we can go through the docs one, so like everyone will be able to understand like how what properties we can use for what type of instances and what type of conditions.
yeah, okay. Sure, no problem. So
Yeah.
the two most important ones really are this one and the invariant. So invariants allow you to write properties about like the generic state of the contract. So these are mostly about, oh, this variable should relate to that one. So these are like about the consistency of the state. Then if succeeds properties are more about how state is allowed to change. So in this case, we're saying, well, if this is the case, then no change is allowed. But you could write other properties. Let's write one right now. If succeeds, we can say something like this. Wow. So this property says, well, the balance of the recipient should be the old balance plus the value. There's actually ChatGPT or Copilot wasn't perfect in this case because this is only valid when we're sending tokens to someone else. because when we're sending tokens to ourselves, again, nothing is allowed to change. So if succeeds properties are for describing how change works, invariants are about generic statements that are true in a single point in time. Then we also have something really cool. Let's say you have an owner variable, and you have some very specific logic around the owner variable, and you want to check if it works. You can write properties right on top of the owner variable, and here you'll use if updated. Yeah, so in this case, a very common property that you would write about the owner variable is that only the owner is allowed to update who the owner is. So we can say something like sender equals old owner. You usually would write some more specific property here. But gives you a good example of how you're able to kind of hook into all the updates to this variable
Yeah.
and add specific checks. So you can say things like someone's balance should never go below 10. It really depends on the business logic of your smart contracts, what you would want to write here. And in this case, well, we just want to make sure that it's always the owner that's updating this value. We can add like a little edge case saying, well, the owner might be the zero address, which is the case at initialization. So this is kind of the property that you would write. Yeah, those really are the
That's
main
pretty
ones.
cool.
And these like allow you to check so many things. It's incredible. Yeah. Any questions in the meanwhile?
Yeah, thanks a lot for that. Yep, thanks a lot for that. And I don't think we do have any questions here. Like, if you have anything, like, we can surely continue.
No, no, that's it. I would recommend everybody to try out fuzzing. I guess there's one more thing. So there's different ways of writing like properties. You can write properties as your test cases. In your test cases, as I described at the start of this, you can write them in Scribble properties. Actually, one cool thing is the instrumentation. You can have it use assertion statements. Which means that your unit test will also be able to trigger property violations. So writing this property instantly enhances all your unit tests to now also check this property. That's a really cool thing. But this is not the only way to write properties, and it's not always the easiest. So one thing we're working on, and we're probably gonna release very soon, is compatibility with the fuzz test format that DevTools introduced, and that's
Yeah,
also adapted by Foundry, which is like you get to write essentially your fuzz test is simple solidity functions. You give it some arguments, and then the fuzzer fuzzes those
yeah,
arguments, and you get to do tricks with cheat codes, for example. Usually, cheat codes are kind of a replacement. Like they allow you to do some of the things that Scribble allows you to do. Not like I think Scribble in the end will allow you to do more things, but pretty soon we're gonna release this where you're essentially able to run a fuzzing campaign both on your Scribble properties, but also on your Foundry fuzz test. So you can still access kind of the fuzzer or the fuzzing engine that we've built, which is incredibly performant and has so many optimizations that are not present in open source fuzzers at the moment that allows it to like find more edge cases in a shorter amount of time, which is like it will find more bugs in the end. So yeah, um, I guess that's it.
All right, all right. So thank you, Joran, for joining us, and thank you everyone for being here. So, like, do subscribe to Developer YouTube channel. Like, we host weekly workshops, and yeah, check out the playlist in the Developer channel over there. And yes, see you all guys soon in the next workshop. Bye bye.
See ya.